Material selection for the handle of a urinal, Group M2 by Mohammed Khalis, Mitchell Uku, and Kieran Wateros. This video will detail the process behind selecting the best material as it pertains to design requirements and constraints.
Pictured is the part upon which we have decided to base our analysis and material selection procedure. This part is the flush handle of a urinal, specifically one which is located in an E2 men's washroom. Before the picture was taken, the part was cleaned to ensure that any visible imperfections were corrosion or wear based as opposed to simply grime. This part is made from a material that is iron based, which is evidenced by the reddish-brown oxide at the base of the handle. This part also has a shiny silver coating, which is likely chrome and intended to prevent corrosion. Several types of corrosion are in evidence on the part. Firstly, some pitting corrosion is in evidence on the ball portion of the handle. There is also uniform corrosion occurring at the point at which the handle joins the ball. Lastly, there is mechanical wear occurring along the handle where the part is normally grabbed.
Corrosion is a chemical reaction with components of its environment. In the case of our observed parts, there is constant exposure to wet, warm, salty, and oxygenated conditions, consistent with that of a male washroom. Our observed part was iron-based and chrome-plated to resist corrosion. The dissimilar metals used makes our parts susceptible to galvanic corrosion, as iron and chromium have different electrode potentials, with water and moisture present in the environment acting as an electrolyte.
This slide shows the functional requirements of the aforementioned urinal handle. Functional requirements are related to machine performance, which are governed by various constraints. The functional requirements we have chosen are that the handle must not bend, indicating stiffness, handle must not break, indicating strength, must be resistant to scratches, indicating hardness, the handle must be corrosion resistant, and finally, it must be relatively simple to manufacture.
This slide shows the selected design requirements and geometrical constraints. Design requirements relate to the ideal characteristics for the urinal handle to be durable and effective when the constraints are based off of standard dimensioning, which is ideal for public use. The chosen design requirements are a yield strength greater than or equal to 30 megapascals, a stiffness with a Young's modulus greater than or equal to 1.5 gigapascals, a Vickers hardness value of greater than 60, and a Pilling-Bedworth ratio between 1 and 2. The selected constraints are a handle length between 5 and 6 centimeters, not including the ball pivot, a handle diameter between 1 and 2 centimeters, and material cost of less than or equal to $1 per kilogram.
The Material Performance Index derivation is used to validate materials selected for final design. The material characteristics highlighted were volume and strength, both being crucial to final cost and sound engineering design.
Over the course of 5 distinct tests, the CES software was used to narrow down our material selection to 6 different materials. Each of these materials was ranked from best or first to worst, 6th, in each of these 5 categories. Each category had a weight factor between 0 and 1 applied to its value to differentiate which characteristics were deemed most important. The cheapest method for the manufacture of many copies of a small part is casting. As such, we compared the castability of each of the 6 considered materials. This parameter was given a weight of 0.2. The best materials in this category are zinc, aluminum, and brass.
In this slide, we are looking at an MPI graph comparing Young's modulus against hardness. The hardness of a material is important to avoid surface scratches and mechanical wear. Since all metals are relatively hard in comparison to what they will be coming up against on a day-to-day basis, This parameter was associated with a relatively low weight factor of 0.1. The hardest materials of those in consideration are stainless steel and nickel. In this slide, we are looking at an MPI graph comparing Young's modulus against yield strength. Yield strength of a material is obviously important to prevent failure. However, at the normal size of a urinal handle and in a normal range of human pool strength, most metals are unlikely to fail. As such, this parameter was weighted at 0.1. The strongest of the considered metals is stainless steel and followed by nickel. In this slide, we are looking at an MPI graph comparing Young's modulus against price. For a mass-produced part, minimizing price is an important consideration. As such, price was given the relatively high weight factor of 0.3. The cheapest materials in consideration are aluminum and zinc. In this slide, we are looking at an MPI graph comparing Young's modulus against corrosion resistance. The corrosion resistance of material is another important consideration for this part. To reflect this, a weight factor of 0.3 was applied. Of the 6 chosen materials, highest corrosion resistance values are associated with brass and copper.
At this point, a spreadsheet was created to rank the 6 options. Also included, though without a weight value attached, was material pilling bedworth ratio. Had any of the selected materials had a bedworth ratio not within 1 to 2, they would have been eliminated from selection. From these 6 materials, the selected one was brass, as it had the lowest overall score of 2.2. To decide on a specific brass alloy, a level 3 plot on the CES software was used. In this plot, all brass alloys meeting the Young's modulus requirement were considered. From these options, the cheapest brass option, which was designed for casting, was chosen. The chosen material is brass, copper zinc 40, lead 2.
One of the characteristics of brass is that it naturally age hardens at room temperature. This means that the handle will resist scratches without the application of any post-manufacturing heat treatments. The outer color of brass starts similar to gold and then darkens with age. This darker tarnish is the protective oxide coating that is formed. This oxide coating may not form in high handling areas of a brass piece, but the material has favorable corrosion resistance, even without this layer.